So we're going to try and understand what's so what do you think? What's supervised machine learning? Give me samples. What are we trying to do? Yeah, go ahead. Okay, we have two labels, yes. Okay. Oh, this is an amount. Okay, so I'm gonna try, and like in general, my style is, I try to be very simple. So, like if this is stuff that you've heard before, I apologize, but I really feel like I rather cater to those who may have not seen this pedagogically before. And so, it's also the way I like to learn, and so I feel like this sort of reflects on what I do. So my understanding is that you heard a little bit yesterday about sort of general machine learning concepts, yes? Okay, and you also had an introduction to unsupervised machine learning, yes? Okay, very good. So we're gonna try and supervise. We're gonna try and I have to be here. All right, so we're going to try and understand what's supervised. So what do you think? What's supervised machine learning? Give me samples. What are we trying to do? Yeah, go ahead. Okay, we have two labels, yes. Okay, very good. So let's say we have two labels. For some data at least. And what are we trying to do?
Associate the data to the labels.
Associate the
data to the labels.
Associate the data to the labels. Very good. I like this. Connect. Data. Is there another word that we can use for data to make sure that we are talking about input rather than output? Something like, sometimes we call it variables, in machine learning jargon, sometimes we call those features, right? So these are, sometimes, I think I like to think of them as variables, like or input variables, but these are the kind of things that we expect to know for every object. Even in the future, when we take new data, these are the kind of stuff that we expect to know. So I'm gonna call them features because this is the features, but just to make sure this is data or variables, right? According to whom you ask, to the output. So this is already telling us something. Yeah, or to the label function. Yeah.
This might be going too far and off track, but is there a sense of confidence associated with labels? Like maybe you're trying to classify something, you have it's candidate this, candidate that, or secure this, secure that.
I mean, this is definitely, this is, I would say, when we formulate the problem, like we usually start from the assumptions that we have at least a subset of objects for which we know the ground truth. And just this tells you like, okay, we start from saying these labels are secure. Clearly, in most cases, right? And sort of like, especially in observational science, this is actually not the real situation. And so we, even those ground truth labels, what we are calling ground truth is not really a truth. It comes from some observation. And so it has some confidence associated with it. And this means that we should actually take into account this uncertainty. I would doubt today we're gonna get to, how to do that, but it's a very important point, right? We are setting this up as we know the truth, but I mean, you know enough to know that really, we almost never know the truth, right? We just have some description, the kind of works, and we have some confidence associated with it. So in fact, this is a good observation. We can put on this truth to remind ourselves that this is really a working assumption rather than the truth. Okay, so very good. So we have true labels from some data. We want to connect the features, which are the data and variables, to the output, which are the labels. So this is good just for jargon purposes, right? So if I imagine writing my data set, right, line by line, these are each example is a row. Yeah, so these sometimes are called instances. These are the features. Then the thing that I want to predict. Yeah.
Sorry, the red is really hard to see.
Okay, no red. Okay, so I'm gonna write these features. Okay. Here, what I wrote here, I'm gonna rewrite it in blue instances. And this is how we call each row in our data set, each object or example. Is it better? Okay. So sometimes objects, samples, for examples. Okay. And then here we have these labels. And so our goal here, maybe I can use the red just for symbols. So this, should be like a little bit easier. Our goal here, as we said, is to be able to connect features with labels. Now, you also told me, okay, for some data, we have the true labels, right? So this is like, I think the most important concept in supervised machine learning is that what we do is we learn by example, right? So, we have, we want to be able to make this connection. Which really means that our goal is that if another object comes around, and for this new object, I know the feature, but I don't know this label, I want to be able to use the relationship that I have derived looking at those examples in order to predict what the label will be for this new object for which it is unknown. Right? And so the whole idea is like, I want to be able to predict an input-output relation where input is features or data or variables, right? You can call it in a different way. Object by object, right? So given the features, which are some observational properties usually of some objects, I want to be able to predict this mysterious property or label, which we still haven't talked about. We can think of this as a label like a class or a number. And we do so by looking at a bunch of examples, using them to derive the relationship, and then we are able to do this also for a new object. So far, so good. Okay. We're happy because we learned this.
Can I ask?
Yes.
Is using emulators also a supervised machine learning?
Using emulators is definitely a supervised, it's like it's one of these like advanced things, but the idea is the same. You need to be able, when like emulators are often used to be able to, sort of accelerate some process. But the idea is always the same. You have a bunch of objects or a bunch of, like input variables for which you have something calculated, something like the result of a cosmological simulation. Now you want to be able to predict it, so now you can do this fast without having to rerun your simulation. So this, applies to very simple problems, but it also applies to very complex problems. It's always the same idea. You have a bunch of objects for which this is known, you use them to learn, and then you're able to make a prediction. And I think something that is important about supervised machine learning is that this prediction is really object by object, right? If you talked about unsupervised learning yesterday, you probably thought about global patterns in the data, right? So not the property of each of the instances in your data set, but like globally, what can I find? What trend do I find? How do they cluster together? Things like this. Here we are considering every object individually, and from its input variables, we want to be able to predict this thing. Now, just still for jargon, this subset of data for which I know both the features and the labels has a name. What do we call it?
Training set.
So again?
Training set.
Training set, almost. We will, we need one further subdivision to get to the training set. All right. This is a learning set. It will be used to train this model, which means to derive the relationship. But we also need to use it to test the model. If we have some parameters, we need to use this learning set to optimize the parameters. So it is for everything. Yes.
So can I interpret like this is a mock data?
Can I use mock data to train my model? Absolutely. Well, and in fact, this is, in many cases, this is all we can do, right? Because, I don't know, for example, if you work in cosmology, you want to learn something about the history of the universe, you really have no direct observation for that. And so learning from simulations or mock data is very common. Now, can you think about any problem that would derive from that? Yeah, from learning from simulations and then trying to learn about the real universe. Yeah.
Any way that your simulation is imperfect, you just learn about your simulation instead of learning about the
Right.
universe.
So this is, a huge problem, which, we have, I feel like, I've lost a lot of sleep on this. Sometimes this is the best that we can do. But, if your simulation does not look like the real world, if there is even like, a part of this feature space where your simulation doesn't work and you don't know, you're gonna overestimate the confidence with which you have learned things. So you have, if the domain, right, which just means like the range of the features that you're using for learning is not the same as your application domain. These are all things in which the relationship that you have learned is not guaranteed to be valid. I mean, in general, it's not guaranteed to be valid, but even more so when there is a difference between what you used to learn, right, from a statistical perspective and your application. So, doesn't mean that we shouldn't do it or it's not valid, no? But I think we just have to be very careful in stating what are our confidence beliefs about this. Yeah.
In the cosmology, that's sort of your training sense, learning set. Is that mitigating effects in any giveaway?
Absolutely. So what really mitigates the effect, like this is like your ideal case, right? Let's say that you have your learning set. Your learning set is where you have, you have confidence that, within the limit of your algorithm, of course, they're not perfect. And, maybe you don't have all the information, but let's say that you feel like you have built this relationship, right? And you have, reasonable confidence because the learning set, as we will see, also gives you a sense of, how well you have learned. Now, the whole thing is that if, let me make this in a 2D space, right? So let's say that you only have two features. We will call with great originality feature 1 and feature 2. Right? And so if this is, all right, if this is the domain of your learning set, and so this is defined by the range, right, of like all the values and by a certain density. Ideally, what you typically want is to have like a uniformly sampled domain, which means that the objects that you're using to learn are sort of covering your learning domain more or less uniformly. And then, as long as your application set, let me see, I'm going to use red for this just to have another color, but if it's not very visible, let me know. as long as your application domain is inside or not very far, you can usually be pretty confident. And so the idea, for example, there of using both simulations and data means that the statistical properties of your learning set and your application domain become closer. Right? So, there's a matter of range, but there's also a matter of like distribution. And so while it's pretty easy to make sure that the range is similar, the thing that happens when you learn with simulated data is that the distributional properties would not be the same. So, the closer these two things are from a statistical perspective, the more confidence you can have in what you have learned. All right, yeah, Asha.
In terms of statistical properties too, does it matter if you train on a learning set that has, say, high signal to noise, but your test or your application set is low signal to noise, or vice versa? That matters.
I mean, I feel like to the question, does it matter? I'm sure that the answer is yes. Now, how does it matter is what I'm not sure. Let me think about it. I think this is like a very good question, also a shallow one, right? I feel like it's tempting to say, okay, if you have a training set, I mean, sometimes the noise properties and how they propagate from high to low signal to noise are actually non-trivial. So I would say it matters, but I would need to think a bit more to think. I think there are several ways in which it can matter. So like what I'm saying is like it's tempting to think that if you have trained in a high signal to noise scenario, then you know this relationship with confidence, and then when you apply to a domain that has lower signal to noise, it's just a bit diluted, but the ground truth is still there, just sort of like convolved with more noise. And so, like I think on paper, this seems okay, but I'm not sure that there are more subtle effects. And then definitely, as I'm sure you know very well from, like even work on photometric pressures and things like this, when you learn in a situation of low signal to noise, right? And then you are trying to apply this to, a domain that has higher signal to noise, there may be effects that are emergent that you have not seen, sometimes what we call latent variables, right? And so this is definitely more complicated. But in general, every time there is a difference in the range and distribution of statistical properties, it means that you have to be extra careful. Yeah.
Do you mind if I add another thought on that?
Of course, no, please.
So another thing that I'll add is that specifically in the context of astronomy, high signal to noise relative to low signal to noise is strongly correlated with distance. And so when you are training on high signal to noise, you're almost certainly training on things that are closer to you than the things that are farther away. And because space is three-dimensional, when you go farther away, you get a huge factor of volume increase. So that's another thing to think very carefully about. So if you, for example, Sloan, which came up yesterday, if you look at the galaxies that Sloan observed, the spectra that Sloan has is of all low redshift galaxies. But we know that galaxies evolve with time. So if you then want to apply models trained with Sloan spectra, low signal to noise photometry, you are sampling different types of galaxies by changing the signal to noise. Now that's not true in every field, but that is a more or less constant truth in astronomy.
All right, thank you so much, Adam. That's a very good thought. Okay, so now we have learned that what we want to do is to learn to predict object by object these mysterious labels. Now there are typically two big subsets of supervised learning according to the nature of the label that you have. Any idea? Yes. Classification and regression. So this is classification. Regression. Very good. What's the difference between these two? Is the difference in the features or in the labels? In the labels. So in classifications, the label is what? So again?
Some integer value.
Some integer value or a class. So I think the idea is like it's a class. I like to think about it sort of like as a discrete output. Right? It could be like an integer value, like 0, 1, and 2. Well, this is usually how we represent it. It could be, you know, red or green. It could be Monday, Tuesday, Wednesday, whatever. Right? It could be, in fact, you know, like even have an infinite number of outputs, as long as they are discrete. Right? There is no contiguity in the output value. And as you probably have figured out, in regression, the label. And in this case, we don't tend to call it a label just for this reason, right? Because it's actually a number typically is continuous. Is spelled correctly?
I think so.
Okay. So, all right. For example, a number, right? 1.756. Like if there is no, this of course is often also a number. Could it be 1.756? Yes. But more usually, you know, this is a continuous value, which means that really like there is no set of values that you predict. You can actually go anywhere in between. So the only difference between classification and regression has to do with the labels. Like the features, if we want to say, okay, what is this? We don't look at them. And of course, sometimes you can solve, you know, a problem. We will think about it. Like hopefully we have a little bit of time to think about examples. Actually, can you give me an example of that you have seen of classification and regression? Yeah. Using photometry to predict redshift. Do we all know what photometry is? Right? Photometry is some observation, usually come from telescope, filters, and so it gives us the brightness of objects in the sky in some range of wavelengths, and to predict redshift, which is a measure of distance. And in this case, would this be classification or regression? Regression, right? Because the redshift typically as a measure of distance is a number. It could be 1, it could be, you know, 1.25, it could be 0.007. Like we have no limitation. Can you imagine having, you know, a similar problem that we instead solve as regression, as classification, sorry. Can you do photometry to do classification? Can you use photometry to do classification? Yeah. Galaxy morphology, spiral, elliptical, very good. Like sometimes, you know, it's like similar kind of data. You're still like taking brightnesses of objects in the sky. You're using for this. Even sometimes with redshift, you know, sometimes you want to determine redshift, but sometimes you're looking, you know, you want to select maybe objects that are at high redshift, and you tend to have these interlopers that, you know, like they are somehow, you know, they can be mistaken for high redshift objects, but maybe are closer. And so in the end, you know, you're trying to say, okay, is this a high redshift or a low redshift object? Not necessarily trying to pinpoint exactly the value, but just saying, you know, which class do you belong? The class that I'm interested in or the one that I want to throw away for the time being? So there is a lot of ambiguity between these. And as we'll see, sometimes, you know, it may seem obvious, but sometimes it's not clear whether or not you want to solve a problem as classification or regression. Something that I always think about is that, you know, in classification, this is usually simpler to evaluate. As we will see, the metrics for classifications tend to be simpler. There are just fewer of them, right? But regression sometimes retains more information. For example, for this, like, you know, let's say that I want to say, okay, are you the high redshift galaxies I'm looking for, or are you merely a low redshift interloper that is disturbing my sample? I could solve this as classification, say, okay, you go here, you go there. But I could also solve it as regression by predicting, for example, the probability, right, that the galaxy is higher or low redshift. And which one of these has more information? The yes, no, or the probability?
Probability.
Probably why?
More resolution.
More resolution, so the probability retains some idea about the confidence that I have, right? I think in the end, if I'm just using this to select objects in a sample, the effect is the same. But the probability gives me a lot more options. Like one, because for example, if I know that the object was classified as high ratio with 90% probability, this tells me something different than if my probability was 55%. So having access to this information is good. And then also the probability gives me a chance of setting the threshold where I want it. Right? Let's say that I only want to select galaxies for which I'm very sure they high ratio. Right? I can afford to lose some, but I want all of my objects, maybe because I'm following the map with another observation, to be a high ratio with high confidence. Then I may decide to select the objects that for which I'm secure that they are high ratio objects with 80% probability or more. And vice versa, I could be like, okay, I want to be complete, so it's okay, if some interlopers come in, but I want to make sure that I get all of my high ratio objects. And so I could set the threshold lower. So even if, the classification is simpler, and I think there are, great, there is great value in simplicity, but often, like regression approach or something like where I predict the probability rather than a class may be more flexible and give me more information. Okay, so far we know what we want to do. We know the two types of problems, and we have established that we have this learning set. Make the learning set here. Remember, the learning set is all the objects for which all the features and the labels are. Now, as I'm sure you have seen before, should I use all of these to train my model? No. Why? Yes.
You want some way to validate your model?
Right. Very good. We need to have some way to validate our model once it's written. And what do you mean as validate?
To test to make sure our predictions are yielding the correct answers.
Right. We want to know, we want a way, sort of like an independent way of testing whether our model is building correct answer. Because so far, you can imagine that for objects for which your model has seen both features and outputs or labels, this is, it's a little bit easier. But what we really want to say or ask is that, okay, ideally, the reason why we're building a model here, right, learning to predict this relationship, is because we want to be able to do the following. If I'm bringing a new object in and I'm predicting a label, how confident can I be that I can make this prediction? And so this means that I set aside a part of my learning set so that I can use it for this purpose. To say, okay, am I learning correctly? Or at least to give a measure of the performance of my model, right? When we set this aside, it doesn't mean that I'm expecting to be correct all the time. But I want to be able to give a sense of on new objects that the model has not seen before. How would I perform? And this sort of like holy grail of how would the model perform on new object that it hasn't seen before is called generalization error or generalization score. It depends on what they're using to evaluate your model, if it's an error or a score. And this is really what we would like to know. So I'm gonna put it here. Putting here like this because this is really like the shiny objects we are all after. Now, when I set aside a part of my learning set, what I do is I train the model, and then I predict how it does on this part of the data set that it has not seen before. And so the part of the model, sorry, the part of the data of the learning set that is used to train the model is called training set or train set. Right, this is to build. And then the part that I'm using to see how I'm doing is called test set. Very good. So this is used to. And so if when I apply my model to objects in the training set, I can calculate the train error, right? Or it could be a score. If I'm using something where lower is better, it's an error. If I'm using something where higher is better, it's a score, right? It's nothing. And then when I apply this, when I apply the model train here to objects in the test set, I get the test error. Or score. Now the thing is, are these two things the same? Will they be the same? In principle, the generalization error is how I expect my model to perform when I apply it to an object that it has not seen before. And this is also true for objects in the test set. The model has not seen them before, and I'm applying a model built on objects from the train set. So do I expect that they will be the same, or there could be issues? Yeah, throw it around.
Issues could arise if the systematic way you're getting your learning set and the use case of the model are different.
Right.
If they're the exact same distribution.
Exactly. And so this is the thing. This is, I think, this is a reasonable approximation. Forgive me, I'm going to use. So this is, what I'm doing here is to say the test error is a reasonable proxy for the generalization. Right? And this is why this is what I'm after. This is the best I can do. However, keep in mind that here, we have our learning set. Right? So the statistical properties of the test set come from this. And so once again, if the domain of where I trained or tested and my application domain, the object I really want to use this for, is exactly the same, then this is a fair substitute, right? It's a very close traceable. But the moment I move away from that exact distribution, this becomes a proxy that is less and less believable. And actually, the part that is tricky is not just that we lose some of this performance, like we cannot be sure that the model behaves the same way, but the fact that it's very hard to quantify how much worse you do as a function of like how you're moving away from the domain. This is another problem that I've thought about a lot. It's just something that, again, there's not a lot you can do, but it's always good to keep it in mind. In any case, using this as a proxy for this tends to be optimistic, because your new objects are never going to be exactly drawn from the same distribution. But you can do what you can to make sure that like you look at the statistical properties of your application domain and learning domain, make sure that they're reasonably correct. You state when you're moving out of the domain, you keep this in mind as a caveat. And then perhaps there's also other things that one can do to figure it out. But just to say, this is this gives us a train error. This gives us the test error. But really what we're looking for is this quantity which is distinct from this. Okay, one other thing that I want to mention is that in this learning set, we have learned this division between train and test. Typically, this is done, in a statistical fashion. Many of the models that we consider actually have parameters, sometimes they're called hyperparameters, that can be tuned, which means that you can build, for example, one that we will see today in sort of the practical part is one of the simplest, but I think nicest models, which is KNN, K-nearest neighbor. Right? And this is a simple model in which, in order to make predictions for one object, you look for other objects that belong to the trained set that are similar, which means that the distance in feature space is small. And then you say, okay, I'm just going to assume that if these two objects are close in terms of feature values, then also the value of the label will be similar. And it's called K-nearest neighbor because K is a number, and this is how many neighbors do you want to include there. You can do 5, you can do 10, you can do 2, you can do 6, right? And in general, what we do to choose these parameters is like we try different values, and we choose the one that gives us the lowest test error or the highest test score. Now, the problem here is that, let's say that I have done this like in a train and test split for several values of my parameter K, for 5, 10, 20, whatever. Right? And then I choose the value of K that gives me the highest test score. This is totally fine. This is what I'm expected to do. Do you think that now it is fair to use that test error as a proxy for the generalization error? Or do you feel like that these test scores know a little bit more than what would happen in a totally new case? Can I say that if I've used the test set to choose my parameters, is it fair to say that these are objects that my model has not seen before? Not really, right? Because even if I'm not using still the model, I've used them to choose the best parameters. When I go to new objects, there's no guarantees that those best parameters will hold. Well, actually, the best parameter will hopefully hold. But again, like the very reason why I chose that value of K is because it gave me the highest test score. So this whole thing that now objects in the test set are equivalent to new objects that, like I've never seen before, false. And this means that in general, you want to have not 2, but 3 partitions. And so what we tend to do really another color. Please don't trust the relative sizes. They're not quite right. Let me just make them a list. So this. And let me see if I can move things down a little bit. Yeah.
We track on a purple.
Oh, wow.
Which might
Okay,
be
let's
easier
see.
to see.
Yes, that's lovely. Thank you. Let's see. Let's see how we like purple validation. How is it? Very good. I have to say, the aesthetics of this red and purple is bothering me a little bit, but it's okay. I will live with it. And so for this validation set, we use it to pick the values of the parameters. Actually, let me write this as pick parameters. I can still have my and so this means that still the training set is only used to build the model. And I can do this for different values of these parameters that I'm trying out. I evaluate the performance of the model for each value of the parameters, like in this case for each k on this validation set. And then I pick the model that gives me the highest validation scores. These are still not used in building the model, and so this is still fair. But then if I want to have a fair estimate of my generalization error, I need to go one layer out and go to the third partition that I have not used yet and that has not participated in either building a model or picking the parameters. And this is now like a fair proxy for new objects. Like I really haven't used this for anything. And so this is how I can still build a reasonable proxy for the generalization error, even when I'm in need of optimizing parameters. So very often you will see this sort of like 3-tier structure: train, validation, and test. Do you need, yeah, please.
Train error is like the error of that train data, and the validator gets related with the parameter of the data.
So what happens here, what I'm doing, so this is all the learning set. For all of these objects, I know both the features and the labels. The training part is used to build the model, right? And then when I want to choose a parameters, what do? I need to go on a part of my data set that has not been used to build the model and say, okay, for k equal 5, for k equal 10, for k equal 10, 20, what are the scores that I get? And this is what I'm estimating here using this validation part. So this is to estimate, to pick the parameter that gives me the highest score. But then, because it wouldn't be fair to compare the objects that I've used here to totally new objects who don't know anything about the hyperparameter optimization process, I need to get yet a third partition to estimate how the model that I built here for the optimal parameter that I've chosen here, looking at the one that gives me the highest validation scores, behaves on completely unseen objects.
Those errors are related, like all are different.
They are all part of the learning set, and usually these 3 partitions are chosen at random. Right? So you can think of this as, I had my learning set, which is all the objects for which both the input and the output is known, and I just split it at random in 3 parts. Now the sizes of this, it depends a little bit on how much data you have, what you want to do. It could be like maybe 50% for training, 25% for validation, 25% for testing. But just to say, when you see, and especially in deep learning, in fact, I have to confess something to you. I don't really use this that often because the situation in which you want all 3 is when you have to give an estimate of the generalization error. When you want to be able to say, okay, I have built this model, and on my application domain, I expect to perform at 80% accuracy, for example. Sometimes you don't have to do this, right? Sometimes you're just looking for a model with the best parameters, but maybe, you're not, you don't need to give an estimate. In this case, 2 of these work. And so when you work in non-deep learning, which is mostly my case, this is often sufficient. But I think, like the moment you move to neural networks, this structure is very, very common, and that's why I wanted to make sure that you know why it's there. Why does it say train, invalidation, and test? And this is the reason why it's there. Does it make sense? Okay, one last thing that I want to mention. Maybe I'm gonna erase this part of it. How is it been so far? Are you able to see the board? Yeah, okay. So one last thing that I wanted to mention is that when you do this structure, let's say, let me make it for simplicity. Train and test. This is appropriate when you're just choosing parameters or when you're not choosing parameters and want to give the generalization. So if you do this, you choose one partition as your training set and one partition your test set. And usually the way to do it is like, you shuffle your data, unless it's a time series, in which case you're not allowed to shuffle, but most cases you shuffle your data and then you take, the first 70–80% for training, the rest is for testing. So this gives you a point estimate of your train error score and test error score. And a lot of the diagnostics of models, as we will see, rely on comparing these train and test scores. So when you only have a point estimate, this can be a little bit tricky, right? Let's say that you find that one of them is 0.8 and the other is 0.75. And so usually, like in the books, they tell you, okay, if you see a difference, you do X. If they're similar, you do Y. But 0.8 and 0.75, are they similar or are they different? And so in general, something that is good practice, if you have the computational resources, is not choose just one partition, but do this several times. Right? And so, for example, you could do something in which now this is your test. This is the train. Or this is why I have column. I'm gonna make the test set blue. So what I've done here is that rather than choosing only one partition and build a model and test, I've done it 4 times, sort of rotating which part of the data is my test set and which part is my training set. This is something very common, it's called k-fold cross-validation, where fold is another name for partition and k, as usual, is just something that means a number. So in this case, what's my k? 4, right? I've done 4-fold cross-validation, but in general it is k. Validation. So notice that this gives me 4 different test scores. Right? So this will give me the test scores number 1. 2, number 3. What do I do with these test scores? Which one is the test score that I can quote? Should it be one in particular? Should it be the average? Should it be the worst? Just to be on the safe side? What do you think? Say average. Who agrees with average? Yes, average is great. And the reason why we can only pick the average is that, this, like anything in statistics, this should be a random process, right? So maybe this model does incredibly well on the test set, right? But in reality, there's no guarantee that, new objects that we're picking that we want to use as our application domain look like this test fold more than this test fold, or this test fold, or this test fold. Yeah.
Is it normally done as a weighted average, weighted according to how representative it is of the learning set?
Well, if this is picked at random, then the representativeness is the same, right? There is no way to privilege one over the other. If it's true that one, set of the data looks more the application domain, then the best thing to do would be to only train on that, right? So in a way, but typically what we're assuming here is that, the way that those test folds are chosen are random. And so we expect that each one of them could be one particular representation. We know that there will be differences, right? And this is particularly true when you're looking at things like a classification model that is very inhomogeneous or, like imbalanced, right? If you have, for example, like, a big basket with stars, and every now and then there is a heart, right? And you take, a sample set that's like a quarter of the size. You may find out that in your little basket, there are no hearts at all, if they were rare to begin with. So this is called sample variance, right? So in general, the smaller your data set and the more imbalanced, the higher you expect the statistical difference between these sets to be. But these are all statistically equivalent, which means that the only way I can combine this information is doing an average. And the average is good because, well, first of all, it tells me what to expect typically. Just 1 second, I finish this other, come back to you. And then the other thing that is very important is that it gives me a sense of how much the test scores can vary. Now, it is a bit ambitious to calculate something like a standard deviation from 4 numbers or 5 numbers, but we still do it. And this is nice. Why? Because now, if I'm comparing 0.8 and 0.75, but I can say plus or minus 0.05 or 0.1 or 0.001. Now I can tell whether that difference is statistically significant. And this, I think, in my opinion, is like why this is very good practice. Because it gives you not just a sense of the typical performance, but also how much you expect your scores to vary just because of the variance in your data. Sorry, I had her before and then I'll.
Yeah. So if we use the average for the test score, which model do you say to use?
This is a fantastic question. And the answer is none of them. Because it took me years to understand this point. And that's why I'm so glad that you asked this. So none of this model will be the final one that you build. The final one, you build it on everything. The only reason why you do this process is to be able to have a quotable error, a quotable generalization error. But at the end of the day, there is no reason why you want to throw away any of data to build the model. Your model will be, in fact, enhanced by using more things. But then, to say, so your final model will come from a training on the whole thing. But then to say, okay, how well do I expect my models to be? Then you use this test.
It's basically the same question, but I was going to ask, do you have different hyperparameters for all these?
Well, if I have different hyperparameters, you will have to go back to our lovely validation set. And this becomes trickier because to do this properly, you need to have 2 levels of cross-validation. So this becomes nested cross-validation. So basically, you imagine that now in this fold, you carve out a validation set. And so you could do it this way. To do it properly, this should also be rotating so that you actually have a sense when you create your validation scores and how much they vary and what confidence is associated with this. So this is something that one can do for a small data set, and that's why I feel like in non-deep learning, this is relatively common. But in deep learning, and like the experts here can tell me more, this is rare to see, and point estimates are more common. But if you have to do it, yes, then you should do nested cross-validation to do things properly. Yeah.
I was just going to ask how you know that you're not overfitting each target.
I'm gonna get to this right now.
Okay.
And by the way, guys, we have another half an hour. Do you need a 5-minute break? What do you think? No? Good? Yes? I don't know.
Okay. Let's take a 5 minutes break and then we'll come back. Which two are you coming what are you working on? Sorry,
I think I do listening systematics.
Oh, I see.
But I don't remember either.
Yeah, I do it.
What was plans?
All kinds of stuff. I would say mostly theories, but I also work with so
there is no hard and fast rule
theory.
with the ratios.
And you said that you like raise your hand when you ask me machine learning, like so that's much better.
I don't really use machine learning.
Yes.
I use Gaussian processes. So it's not really like, I mean, it is kind of complicated, but I don't do like
find the sweet spot
as
much as possible.
What about you?
Not at all. Like other people,
So you may have to experiment and stuff.
Yeah.
Once you find the
So-
test score stabilized,
I only like half understand those talks, so it's like nice to actually get this like
Yeah, for sure.
background.
Yeah.
But yeah,
Yeah, I'm
learning
not
a lot.
really, yeah, I'm a learning person.
yeah.
I'm trying to be. So I want to use more. I want to utilize it more.
There's
But,
another, sorry, 1 second. There's
Another
another
bad-
thread.
So,
One of the person.
yeah,
One of the
like
person
hopefully
that they
you'll
have
get
Oh, wonderful.
Yeah, I think it'd be really useful to just like show that you have
Of
that
course,
skill.
yeah.
Yeah. Well, I do have like a project where I'm going to. I feel like I still feel like this session would be a good introduction, but like, definitely it's not going to be enough to do research. But I have the project, so really cool. Yeah, there's like a bunch of people working on this like, yeah, Brandon.
I only got to like figure out what people were doing in the second year cohort of teaching.
Yeah.
So, I haven't talked to them like
Yeah, I also
Yeah.
I only know like from the field because
I feel like
yeah.
Exactly.
I'm not for
point by point when you add that this is connected to the list, then it's the projection.
How do you like Chicago?
But it's nice.
yeah. It was a little bit like overwhelming at first, just because I've never lived in a city before, so it's a lot of busyness, like moving fast and drivers doing whatever they want. But
Yeah.
it's a lot of that, but it's good now. I actually like the pace.
Yeah, you can do that.
I love New York.
I mean, like, that's like the city, right, in America.
Yeah, but also I feel like for some people it could be really overwhelming. For me, it's fine because I grew up in a city. So for me, it's like actually preferable to live in a city. I think I figured out I'm more like a city girl.
What city are you from?
I'm from Kazakhstan, so I'm from
where?
Kazakhstan.
Kazakhstan. Oh, okay.
Yeah.
I thought you said Kazakhstan. Yeah. I was like, where about it?
Yeah, so I'm from Kazakhstan. Yeah, and it's like, I mean, it's not as big as New York, but it's a city, like relatively big. Yeah, so
that you would be getting
Yeah.
I feel like you are probably not the most like person, just like from the vibe.
From the vibes,
Yeah.
yeah, I don't have to say vibes.
Like, yeah, it's like I don't know. It's like, do you think you're like more extrovert or like introvert? So yeah, that's like,
Yes, like
like so yeah, it's like a lot, like chaotic. Yeah,
that makes sense. Like you're talking to a lot of people.
yeah. I'm in general like very chaotic person, so it's like it kind of makes sense that I like the person who's even like small things. I get bored.
Yeah, I don't know. I've always been like shy, and so it's not that I don't have chaos in me, but definitely that's kind of something that comes out like someone else.
No, for sure, yeah.
That's a good.
Where
We have a Discord.
what's your I think you told me that. Yeah.
Okay, so now we have learned how to build the model in our training set. And let's assume, like, I'm gonna set aside the idea of like what errors or scores we can use. Hopefully we'll have a few minutes to talk about that too. But the other thing I want to say is like, okay, diagnosing the model, right? We have built it and we have calculating the test error and we have calculating the training error. And, we can work on like maybe, let's just assume for now that we have like train and test, and these are the two that we are connected. But if you have a validation, it will be like a similar thing. We will be comparing train and validation. So I want to say, okay, now, maybe I wish it for you. It's a classification problem. It gets everything right. Every possible metric you calculate is like 100% correct. But as you probably know, this is not how real life works. And so you will find that you have some performance evaluator, like assessment, and that is set at some level. And you calculate this on the train set, on the test set. You may find that they are different. And so what do we do next? And so I'm going to start with the classic example, which is we are fitting. This is like a one-dimensional problem where you have only one feature and only one output, right? Just so we can say this is input. Output. These are my training set data. Pretend that these are the same. And now let's say that I'm fitting this with different curves. One like this, one like this, one like this. Right, so these are my three options. Now, which model has the highest train score? The last one, right? Because I feel like the prediction of the models, which is like where the model is in red, are exactly catching all the points. So this is a model that has 0 error. Would you say that this is the best model? No, why? It's overfitting. How can you tell that it's overfitting? Yeah. It's definitely learning stuff that is not there. But basically, the idea is like, here we are eyeballing something that normally we don't have the luxury of doing. But this is the whole reason why we're doing this in one thing. We are eyeballing the relationship. And let's say now that, because we have learned that we shouldn't trust the scores, the training scores alone, right? Because the model has seen these points before. And so we can be too optimistic. Let's add points from the test set to this to this plot. And so points from the test set are gonna lie on a similar curve because they are drawn from the same distribution as points from the train set, but they will be in different points. So it will be here, 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 here. Again, please pretend they are the same. Here. Okay, so here, this means that, let's look at this model on the other hand. Is this model performing very well on the train set? No? Okay. So train set error. The higher low. Let me call it high just for simplicity. Right, it's not doing so well. How about the test set error? Also high. Also high. Like sort of like similarly high. That's really the thing. Let me go on this side. How is the train error going to be here?
Oh.
Very low. How about the test error? Okay, so these models have in reality similar problems. The test, like the way that your model is not working well is always looking at the test error. And so they have similar issues. The test error is high and the test error is high, right? This is what we are trying to fix in both cases. But you can see here that by looking at how the train error is, we can try and diagnose whether we are in this situation where the model is sort of underperforming both on the train and on the test set, or we are in this situation where the model is too affectionate to its training set and then is not generalizing well. And this is, of course, the sort of like Goldilocks model where we have train, test, errors, and reason.
Can I ask?
Right? This is where we want to end up. But typically, when you start, you have something that is telling you things are not great, which is the test error is high. And so the diagnostic that you can run to see in which situation you are is, let me compare the test error with the trainer and say, okay, are they similar, which means I'm in this situation, or are they very different? There's a big gap, which means I'm in this situation. Yeah.
I'm sorry, but I don't really see that the first model is like bad. It's like it looks like it is reasonable, and I feel like a lot of like I feel like before we got all of the complicated machine learning algorithms, this is how the fundamental power laws were derived.
No, I think you're right. I think in part it's because like maybe like how I'm drawing.
Yeah.
What I'm trying to say here is that the real relationship is something has curvature, and I'm trying to fit with something that is excessively simplistic. But you're right that this is not that bad. I just want to say, like it is not ideal, and I didn't make this. Perhaps I should at least improve this one a little bit, so we can find out that we're following, the first one with the reason. But yes, it's not that bad. Just saying we can do better.
Okay.
Yeah.
So from the beginning, like we have the learning set, then we are like partitioning train and test data.
Yeah.
And on the train data, we are building the model, that red line.
Yes.
Or fitting to it.
Right.
And then we are diagnosing between the diagnostics and like computing the test, like this error, brain error.
Yes.
So this is the
Yes, absolutely. And then we are also computing the train set error, sort of like this is our diagnostic. It's saying, okay, I have used the points in the train set, which were the black points in this drawing, to figure out, which model I have. And this means that I made a simplistic choice in which models I'm using, right? Because I'm just using a straight line. And here I've chosen a more complex models that is able to catch all my training points correctly, but then it's not generalized well. So, the test error, actually, I should put this in blue, is calculating on the blue points. So this brings us to this, typical cases in which errors in your machine learning models can arise. In this case, what happens is that our model is too simplistic. And this is what is called underfitting or high bias sometimes. It means that the model doesn't have enough complexity to accommodate your input-output relation. Like an example of this is like wanted to use a linear model, which as we have established, are fairly common in astronomy, or like broken power laws, which is like two linear models combined. When maybe there is, like there is more complexity in the relations that you're trying to capture. And this is like the other side of this, which is called overfitting. And I feel like that this tends to be more common in practical situations, and sometimes it's referred to as high variance. Right? And this means that your model has learned not just about the relationship that you're trying to capture, but also some nooks and crannies of your training set. It is too tailored to its training domain. It means that we need to nudge it away from it. And it could be achieved in different ways, but the first step is always to see in which situation we are. And so in many cases we cannot plot. And for this, what we look is the difference between the train error and the test error. Like in general, the things that is, that different models have in common when you're trying to solve the problem is that your test error is high. Right? If it weren't in this situation, you wouldn't be bothering with the diagnosis, right? If your model is performing amazing, in a way there is no point. So what you're trying to solve is always your test error is too high. And then you're like, okay, let me look at the train set error. Is it also high? Which means that maybe I've chosen a model that's too simplistic, or in any case, I don't have enough complexity to represent this relation. Or, am I in this situation where I have a big gap between the train and the test set error, and so I need to work on ways to reduce that. And in general, I mean, as sort of like a general rule, the idea here is that if you're in this situation, you want to increase complexity. And in this situation, you want to decrease complexity. How to do this in practice is a bit tricky. So increasing complexity could be choosing a model, here, like rather than a straight line, we could choose a higher degree polynomial. This is one possibility, but it could also mean that maybe the features that you have are not informative enough. And so maybe you want to engineer new features. This is like another thing that is potentially quite helpful. And in this situation, you could try and choose a simpler model, like here this would correspond to reducing the degree of the polynomial, but you could think about, okay, do I have features that are just like adding noise and not carrying information? Do I want to get rid of them? So you can think about this process in different ways. The first operation in general that helps with both is to tune hyperparameters, right? So from the point of view of sort of solutions. Tuning the parameter of the models is typically the first things that you try, and it's helpful. And you can use this as an indication of, do I want to tune parameters and trying to make my model more complex, or do I want to tune it towards a direction of being a bit simpler? Another things that it could be to create, like engineer or delete features. And then another possibility could be to change algorithm. Right? It could be that you start with something that's relatively simple. In general, I always like to do it this way, but then like you can, if you feel like okay, I sort of like hit the limit on what I think this algorithm can do. Can I sort of upgrade? Can I do something more complex? Can I try neural network or something like this? And this, in some cases, maybe. Does it make sense? Right? So you always look at this as a comparison. And then I would say still on the topic of diagnostics, I want to introduce one last tool, which is called learning curves, which is sort of a practical way of evaluating that gap and also at the same time checking if you have enough training data. So this is something that we were talking about briefly in the short break. So this sort of basic diagnostic tools are slightly complicated by the fact that one other reason that you observe, especially this behavior, could be that you don't have enough training data. Right? This is common in machine learning. Maybe you're working with a small data set. And so you want to learn this relationship, but maybe you just don't have enough examples to be able to capture it. And so none of this solution is going to help, because really where you should be putting your effort is to collect more examples. Right? Or maybe, otherwise, maybe it's just not time for a machine learning approach yet. So how can you tell? And this is something that I always do, that I put in our notebooks that I promise I will upload. So the idea here is that you can create a graph. Okay, and so here you have learning set size. Sort of here on the right, you will have 100%. Right? This is like the full size of your learning set. And here you will put the test. So, the behavior of these curves can be different. But let's say that now you try and do this exercise of computing both the train and the set and the test scores for a given algorithm for different subset of your learning set. For example, with just 20% of your data. Right? And usually you will have the training first. This is call it a score. So far. And so sometimes, the test error, the train error does funny things, but let's say that they won't. First of all, which one do you think will always have the highest error, the test or the train?
Yes.
Error? The test. Even in the best case scenario, typically you will still find the difference. Ideally, it's a small difference. Sometimes there's no difference, but in general, as a rule of thumb, the objects in the test set have not participated in model building, so the error that you made on those is high. So let's say that then you can, if you want. So the reason why I like to do this, and I actually like to do it with a band that is a standard deviation, so that's a way to do it in your notebook, is that this tells you two things. Sometimes for both of these curves, what you expect is that you will start with a very high error if the size of your learning set is very small. And of course, you know, if you're taking, like, let's say, just 20% of your learning set, this means that also your train set is only 20% of what it will be, and your test set size is 20% of it. So you start with a very high error. And then, as you add more training data, so you move to the right in this plot, your error decreases. And then at some point it flattens, right? And when it flattens, it means that you have enough objects that adding more training example to your data set, which means sort of like extending this plot to the right, will not make a difference. And so in this case, what we're trying to say is, if I observe a difference between train and test set error, it is due to the fact that I have high variance in my model, or it's due to the fact that I don't have enough training data. And so the reason why you want to plot these learning curves is to say, have they flattened? And you can sort of like these regimes where, in particular, the test is flat. If it's flat, it means that adding more data will not help. And so you can trust the diagnostic, right? So if the answer is yes, then you can trust the. If the answer is no, then it means that you need to add more training data. So here, the curves are flat. So if we observe a difference, and if this difference is statistically significant, that's why it's nice to have cross-validation, because it will give you a band around the curve, then it means that you should treat this as a high variance problem. But if you find that the curves are still sloping, which means that you are in this regime, then this large difference that you may be observing comes from the fact that you need more training data. And so you may spend a lot of effort trying to solve this that you're interpreting as a high variance problem because you're observing this gap. While in reality, the main problem that you have is that you don't have enough training data. And so I found that, you know, I always try, if I can, to plot this learning curve. So we will see an example in our practical part, because it gives you the two sides of diagnostic advance. One, are your training and test error scores similar or different? Which means that, you know, you will find yourself in this or this other regime. And two, is part of your problem, is the size of the learning set part of your problem, or is it something that you can set aside and focus on other aspects? Yeah.
So on that graph, is the global minimum necessarily?
I'm sorry, can you say it a bit louder?
Sure. On the graph that you drew, is the global minimum then necessarily corresponding to the best set size for your model to get the best performance, or?
I think in general, it's fairly true. Well, I mean, I think deep learning makes things, you know, like a little trickier, right? Even just in interpretation. But in general, what I'm trying to say is that, you know, these tend to flatten. And so you want to be in the regime where they have flattened. And if not, then maybe, you know, when you think about, you know, how to improve the model, you should consider adding more data. This is, you know, all I'm trying to say. It's like, you know, figure out whether you're here or here, right? Meaning whether your learning curves have flattened or are still sloping, just as a way of understanding what can help the most going forward. Yeah.
It's mentioning like if we have small learning set, so adding more data. So if it is fixed, so we cannot add. Is there another way to minimize that gap?
Well, there are ways to minimize a gap that relies on this part. So you can try, but I'm just saying, these are, they tend to be helpful when you are in this situation. You may find that they don't help because of that. So it's just something to keep in mind so that, you don't like bang your head incessantly trying to solve an impossible problem.
Yeah. What about instances wherein the test loss is lower than the training loss?
The test loss is lower than the training loss. I don't know. It hasn't happened to me often. So, and do you think it was statistically significant? Because I feel like, the find that sort of like point by point that this can happen, is totally fine. Right. What I'm saying is, is it something like, is it a consistent behavior? And, like if you choose a different test and train partitions, would it still happen? Because the fact that it may happen, occasionally, I think is okay. And I mean, at that point, usually, you're pretty happy. But I think in general, I mean, if, like, I would be surprised if this was sort of like a consistent behavior, right? If you choose a different set of like a train and test set and this continues happening, then I don't know. It could be. That's why I'm suggesting, if you actually pick a different partition, this should typically go away, right? Because if it comes from sample variance, like, maybe like your train set had a lot of outliers and your test set is like exceptionally well behaved, then the moment you choose a different, train and test set at random, you should see that this behavior is like not there anymore. So similar is okay, but yeah, I feel like it'll be a little bit strange.
If I can add,
Yeah.
At future epochs, at future epochs, the training error will be faster than the validation error. That's right. And epoch training more, but it should decrease faster. Yeah, at future epochs, even if at zero epoch.
In my experience, I have seen where it says that it's worth it exponentials small plus so 90% of them just never work with 10% like that. That's the case for you. So
That the data sets are too small for machine. I mean, not really, but I think it is like the very first question. I think, Andres Muller has this like, really cool, I think sort of like, flow chart. In my result from 2013, so if I could make it old, but it's very cool. And the first question is, do you have more than, I don't know, I can't remember, 50, 100 examples? The answer is no. Then it's like, okay, machine learning is probably not the thing for you. And I think this is like, something good to keep in mind. Not, all problems should be solved for machine learning. And so I think the hardest part to do is like, you can do a lot of things. Whether or not it's the right way, I think it's really a question that we should ask at the very beginning of the process. And I think, when you have a small data set, then, trying to gain physical understanding of your model may actually pay off more than trying to use it from, this is basically some sort of like glorified linear algebra. So, and so, again, if you don't have like enough data to really learn the statistical property by example, it seems to me that, this is where really you should do the physics. Like the most Yes, many of them, none of them I think is like 100% trustworthy, but many. I'm happy to talk about it this afternoon. We're gonna look at some models for which there are some built-in methods, and so I'm gonna see if I can find something. All right, so I don't want to take any more time off your break, so we'll see you at 11. Is that right?
11:05.
11:05.
And as a reminder, people think yes, we talked about it.
Five classification problems, so I can use all of them. All right, are we ready? Yes. Okay. All right. So we're gonna try to do like a practical exercise, so you can have like you can see notebooks where we see some of this stuff. But I just wanted to introduce two algorithms that we will have there. They're very simple. I love them. And one of them is the one that I mentioned already, KNN, K nearest neighbors, and the other is a simple decision tree, which I like it because it's a building block for things that are actually more complex and also more performant. So in KNN, I set up the board, as you can see. The goal here is we have a problem with, let's see, how many features?
1, 2, 3, 4, 5.
How many features? Two. Okay. Right? There are two coordinates, right? And so the number of information that we know for each point is 2. We know the x1 coordinate and we have the x2 coordinate, right? Is this a classification or regression problem? Assuming that I want to figure out what type of objects I'm talking about. Classification. So my input, my output would be like star or heart. Okay, how many objects do I have in my learning set? This is the time. yeah, having 4, 7, 3, 5, 19 perhaps. I may actually have a different numbers on the boards. Yeah, here I put an extra star, I think. Okay. Let me add it also on the other side, so it's around now. Okay, great. So let's see. Let's say that I'm using KNN, and as you can see, for KNN, the idea is very simple. I choose a value of K. Right, so this is something that I have to specify. Later I can optimize, but the idea is like, okay, I choose. Okay, and then for every object, I look at the closest K closest neighbors. And then I do majority vote for classification. And average of their output for regression. So in this case, I don't know, give me a number that you want to use for K. How many neighbors should we use in a place like this? How many would you recommend? 3, 4, okay. I think this is reasonable. Now, why not 10, for example? Because we only have 20 objects in my learning set. And disclaimer, if we have 20 objects, probably this is not a machine learning problem, right? But in this case, the size of your data set is important. The other thing is like, how densely populated it is, right? In the sense of, like how far away do you go? Right? In feature space, if you're looking at 20 neighbors rather than 5. And so this is probably, like what sort of like will give you the initial guess. You want to have enough that you capture a bit more of statistics. Like if you only look at 1, it's easier to be moved one way or another. But if you take too many, then the whole idea of neighbors may actually decay. You may not be looking at neighbors anymore, but just like objects in a very vast volume. So in this case, I would say 3 or 4. Now, this is a classification problem, right? Which means that we're going to look at the 3 or 4 closest neighbors, and then we're going to output a majority vote. So do you think the 3 or 4 would be a better choice? Is there a reason why 3 or 4 would be better? They're proposing 3. Why?
4 gives ties.
Because 4 gives ties, right? This is not a concern in regression, because in regression you would just look at the value of the output and average goes for the 4. But in classification, it's nice to have an odd number of neighbors, because this way you're going to be able to output majority vote rather than having to break ties all the time. And so this means, for example, that for this object here, what I do is like keep making circles, 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 circles. My goal is to actually. Oh, I was so excited about the new markers. Oh no! Oh no! Why?
That's not the first time a new box has been dead on arrival. Sorry.
That's okay. That's okay. I have plenty of other ones. And so, where was I? I was at this one, I guess. And so I'm like, okay, bigger, 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 bigger. Okay. So this is not exactly a circle that is centered on this heart, but imagine that it is. And so this means that this is like a very simple determination. I'm like, okay, for this point, if I didn't know about the nature of this point, I would say, okay, if 3 closest neighbors are hearts, and so I'd be like, and in fact, like a better application would be like, okay, if a point is here, like for this point, I don't know if it's a star of a heart, like I make the smallest possible circle that encompasses 3 neighbors, and I say, okay, star, 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 which means that this is a star. Right? So it's a very simple idea. It relies on the idea that if objects are close in feature space, they will also be close in output space. It's very fast. In fact, while in many algorithms, there is a whole concept of training the model. If you think about here, there is no model to train. You're not really building this relationship. However, you will see that in KNN, there's still a part that says, okay, dot fit, which means train. So what happens there is that because you're calculating distances all the time, it's sort of like pre-compute distances so that when the new object comes in, you have a way of calculating the distance from every object and rank them very, very fast. So this is all that it does. And then the other one that we look at is a so-called decision trees. And decision trees are algorithms that are based on questions. Right? So it's similar to games like Guess Who or 20 questions, right? You have your data set and you make partitions of this data set, and this basically corresponds to asking a question about one of the features at the time. So the limitations that you have is that the questions that you can ask or the partitions you can make, they need to be parallel to the original axis that you have. So for example, here, if you want to create a partition that sort of like separates out the 2 types of objects, and remember you can only make horizontal or vertical line. What would you propose that we do? What do you think it should be like the first split that we make? I don't hear a vertical line, okay? And let's say that this is 0, 1, 0, 1, more or less. Where did you put it? Where should I put it? Here, more or less. Right? This is probably something that I make this problem too easy. Let me put something else. Okay, so I make a partition in this, how would we write it? What is the questions that I ask in my decision tree? Am I asking a question about x1 or x2?
X1.
X1, okay. So my question is x1 less than 0.5? I could also do greater or equal, like it was just like a way. A split is basically a question made about one of the features. And then, yes. Then what do you think? Should I continue? Should I be happy with this? Is this like a perfect classification? Not perfect. How many mistakes do I make? 2 out of 21, right? Because I added 1 just to put like an extra mistake. So, this is something that, like it's sort of like a 90% accuracy, right? It's only getting 2 of the examples wrong. But just for the sake of it, let's continue. And let's see, what would it take to be able to solve this problem exactly? What other splits should I make? What other questions should I ask? Yeah. Horizontal cut on the top so I can capture this one, right? Because now in a single partition, I have to make a prediction that is the same for everything. So this is in the case of like, if x1 is less than 0.5, then I can ask, is x2, let's say more than 8, right? Something like that. And then I have yes, no. So if the answer is yes, am I ready to make a classification? Yes. And what do I add? If I'm in this case, what should be my output? Heart? And if that's not the case, what do I add? Star? Okay. How about in this case? Should I make a classification and take my mistake, or should I try to make further partitions? How many questions do I need to get that right? Probably too many. Like I would need to make 1, right? And then I'm still not done. Then I would need to make at least this one. Right? So, this is a decision. This goes back to the idea of like, do I want to privilege accuracy and make my model more complex, or do I want to privilege simplicity and accept that I will make a few more mistakes? So we're gonna get to that, but this is the idea. For the time being, let's say that we can leave it like this, and so in this case, maybe I will give an output, and the output for this case will be heart. And what's gonna be my trained score? If I'm using accuracy, just the percentage of correct answers. 20 out of 21, right? So about 95%. And in general, notice that if I hadn't set the limit saying, okay, I don't think this is working, I can always continue and make partitions that are smaller and smaller and get every single object right in its own box. Probably not the best solution, but an unleashed decision tree where I don't set the limit to how many splits I make, or like I don't sort of like say, okay, what level of inhomogeneity am I willing to take? We'll just like continue making tinier and tinier boxes. Right? So decision tree is basically a set of questions. Actually, let's be a little bit more. Set of partitions, parallel the original features. This is important. In decision trees, just is like in the way the algorithm is implemented. I cannot ask a question about the product, for example. Like the way it's coded, it's like all I can do is making splits that are parallel to the axis. So if I want more freedom, I have to build it in myself. But instead of partition parallel to the features, maybe the goal maximizing works simpler than homework design. Uniformity, maybe. Yes.
Is there like a
There's no mathematical reason. This is really like a coding reason. When you implement a decision tree, it will literally take the columns that you have provided as features and try all the possible splits, right? And only do parallel ones. So if you want to add a feature that is the product or like a polynomial combination, you need to add it to the features. You need to engineer yourself. So it's possible, but this is just the way that it works in this sort of like implementation. It doesn't have a mechanism for feature engineering that is internal, like other methods may have.
so the idea is that you're
Yes, it will only work with the columns that are provided. So you can do it, of course. You can pre-process your data to improve more, but you have to do it yourself. And the thing that we haven't really seen here, we were sort of like just looking and deciding, okay, let me put the split here. As you know, in general, you don't have this freedom because you have like many dimensions, right? And it's not obvious which splits should come first. So the way that this is done is that you sort of like select the split, sort of like find some information gain right here. We find some, we call it uniformity gain. And you use it to rank all the possible splits. Right, so when you implement this in a scalar, which is what we will do next, what it will do is it will consider all the possible splits. Now, the possible splits are infinite, of course, but because you have a finite number of objects, you can imagine really reducing the number of splits that you have to something that like single out, objects in different combinations. And this is like a finite number. So it will try all of them, and it will calculate, what's the gain in uniformity that you have. For classification, this is something called Gini purity. For regression, it's just some measure of the variance in the values of the output for given partitions. And then I will give you the split that basically gives you the maximum gain in uniformity. Right? And so this is the way how this split is not great because you're left with two partitions. We're still here, you have a big mix, and this split is better. And so at each stage, you will just ask the questions that gives you like the optimal gain in uniformity, and continue. If you don't say anything, continue until each object is in a box that is completely uniform. If you want to, you can regulate this behavior, but you have to tell it yourself. So far, so good? Okay, I think this is all I wanted to tell you about this. And I put on Slack a notebook that we will work on together for a little bit, and also a data set. And because we have like another longer session after lunch, we're gonna go through some things together now, just discussing, and then you have some tasks that you can do on your own, and we can do this. We'll see if we do this before or after lunch. So let's see. Okay.
We'll get forward. All right. Thank you.
So I'm screen sharing, and so are you guys okay looking at a laptop? Should we project this also here? What do you recommend?
Okay.
Ah, yes, I do have one. So I have.
My page.
Yes.
Everyone can see now.
Okay. All right, so for this part, I thought we will just, think about some stuff together. And so you're welcome to, can you read it at the board? Should I make it bigger? Don't know what you prefer to use. It's gonna be this sort of like Inception-like thing with your looking on your laptop and also seeing on the board, and I'm gonna be talking about this. So, okay, shall I proceed? Yes, okay. So here, these are all the commands you will, in fact, one of them is repeated. So these are just like, okay, some stuff that we will need. And I've heard that you have been introduced to these packages. And, if you look at these lines, are they at least in a familiar form? Okay. Okay, so this is, I just was looking for like a new exercise because I've been repeating the same over and over. And so I just, these are data from the Sloan Digital Sky Survey. And it's just a simple classification problem in star, galaxy, and quasar. And the data actually come from Kaggle. It's one of the Kaggle datasets. And because it was a little bit big, it was like 100,000 examples, I just figured maybe we don't want to work with this. And so I just randomly selected 20% of those. Okay, and this is what I'm doing here and resetting it. So, are you familiar with what the data frame is? Is someone not familiar with the data frame? Okay, assuming that you are, it's just like a way of structuring data. It's nice because it has columns and rows just like arrays, but you also have names for your columns and you can access those column by name, so you don't have to remember like is it column 7 or column 8. You can also like mix and match, so it has like lots of nice properties. And so here you can see that if I list the columns of this data frame, I get object ID, an ID not very interesting, alpha, delta, they're probably coordinates of some sort. Then things that have to do with the survey itself, like plate, MJD, Faber ID, blah, blah, blah. The ones that we're gonna look at is photometry. And so these U, G, R, I, and Z are probably something that we will use. And then there is also this class that sounds like suspiciously relevant. And to get some basic information about data, you can use describe. Describe, however, only applies to numerical columns. Right? So I always like to use it because just to get a sense of how the features are distributed, for example, you can look at things like the mean and the median. And in general, if mean and medians are very different, this hints to a distribution that is not very regular. Or you can do things like mean and max, which in themselves they don't tell you too much because the range of different features can be different. But for example, here in the minimum value, do you see something that perhaps suggests that it will require attention? Like this is the minimum values. Do you feel like something that for like our photometry doesn't look too good? Yeah, which ones? Again? These giant negative values. Right? I feel like, okay, this is a very unsophisticated way of looking at things. But I find that, it helps a lot. You look at mean, max, median, mean, and you can see, are they different? Are they the same? Why not? So for our feature and targets, okay, the photometry, we have decided. In fact, I have made an executive decision. Yes.
Also the max, I'm noticing for photometry. That's like an awesome telescope that we can do with it now.
Yes, this is, yeah, exactly. The fact that you can get to magnitudes of like 28, 29 is telling you, wow, this is like very deep observations. But this is already sort of like, expert level. But yes, so this is something that in fact is not worrisome from a data perspective. It's great because this is telling you these are really good observations. So for featured and targets here, what should I get? What features should I pick? Which columns? UGR, IT, I would say, okay, guaranteed. Anything else that can help? Redshift, right? Redshift probably helps because, like if you think about stars and galaxies and quasars, like in the sky, we just see 2D projections. So if you could tell the distance, this would probably tell us a lot. But let's be fair. I think that if you know the redshift, it means you probably know the nature of the object. And so I figured that, especially when you're looking at star versus galaxies. So, I sort of like, I figured that, this is probably something that, had a little bit of recursory information. So I'm going to set it aside because otherwise it will be a bit too easy. So we can just keep the photometry, and then let's see in these columns, which one will be our target, which one is the label that we want to learn to figure out. Class, right? So this one is the one that has star, galaxy, quasar. Okay, so I'm selecting these columns to be our features. And now in general, what I always recommend doing, and by the way, in Slack, I put a little like flow chart that comes from my book. If you want, I can put a link to that also, but this is just something that I find it helpful to look at when I have this like a supervised problem. I put it in general, so I apologize about this instead of in session 19. I feel like the first thing that I always recommend doing is always a sort of like data exploration, right? Even before you start working on this as a problem, like try to get a sense, how do the features look like? Are there like odd things that are coming about? How is the target property distributed? Is it balanced, imbalanced? Does it look funny? Are there outliers? Things like this. And if you do it beforehand, I think it's always saving time in the long run. So what should we do, for example? What's like the classic thing? Yeah.
So question.
Yeah.
Thinking, why would you let
Oh, here?
Yeah, like
oh.
Probably don't care about the object that you have. We're not including redshift.
Yeah. The redshift I'm not including just because if you put the redshift, this is like an incredibly easy problem. And so I feel like just the way that this data was collected, the redshift was probably, so this is the reason, just to keep it more interesting. But in general, I agree with you. A lot of times, I mean, for some of these, I think, we can agree that if every time we add a column, like we make more data, right? We make our data set bigger and potentially we add this. So I think probably where I would be is like somewhere in the middle of saying, okay, for some of them, I think we can very reasonably say they're not going to add information. But for some other, if we're not sure, we could also say, why not? The one thing there is that if we do this algorithm, the effect will be very, very different. So in any distance-based algorithm, for example, KNN, the distance here to find the neighbors, they're calculating in all the features that you provide. And so if you provide a feature that is absolutely useless, right? But because maybe like you don't know or something, then unfortunately that you have no way to exclude this from your distance calculation. And so if you have 5 columns that make no sense, they may actually end up dominating the distances here and what you consider neighbor, even if all they have in common is not that they're similar physical objects, but I don't know, they were observed in the same day. So this is tricky. Here, you actually can do this much more because since this is based on, like looking at information being feature by feature, those features will be simply ignored. So they may still be noisy, they may still, like be acting as a compounding variable. And so I feel like, my feeling is that if you know that they are useless, reasonably confident they will help, then you should still exclude them, but it really depends on what you're using. So I think that's a very good observation. Did you want to say something or add something to this similar lines? All right, so for us, we're just gonna look at these features. And then what should I do? What's the first thing I should do? Especially when I only have 5 of my features. What should I do? A sort of a data exploration step. Plot the histogram, yes. Right? The histogram is like, sort of the workhorse of scientific exploration. So here we go. Okay. What do you think? Is it a good looking histogram? Not really. Right? It's not. I think I plotted like, all 5 columns, like I think like a transparency. So, I was hoping to look at just, slightly different distributions, like, with their personality and stuff. This is not very good. So when a histogram looks like this, what does it mean? When is that the histogram always looks funny like this? Right. When you have like some giant outliers that basically end up dominating your range. And this is in fact the same thing that we have noticed, right? We had this like very large negative number. But this is another good way. If we didn't see it there, this is one way. And this is something that is sort of like a non-pro tip. But in general, when you plot things, and like Python will choose the range of the histogram for you. And so when the range looks funny, it means that there are outliers. And so this is another, again, very non-professional way of realizing that something is good. So if we adjust the range ourselves, right? For example, 0-30, you can see that this really was the problem. And then, other than those objects, our, the distribution of our input variables is fairly well behaved. And so again, there are many better ways. In fact, I had planned to find a better way of doing this selection myself. But here I'm just saying, let me exclude any objects where in any column I have, from the photometry, I have a negative value. There's only in 3 columns, there is, sorry, this is where I did the selection. I was just counting how many negative values I have for each features, and there's really just 1 in 3 columns. So it's a very small problem. Right, so out of the 20,000 objects that I had, I'm left with 19,999. So not bad. And now I can redo my plot. You can say, okay, these are now distributions that are reasonable. Now I go to the target. Right, for the target column, this is something I can use to visualize the values that I have. And so I have galaxy, QSO, and star. Yeah.
So when you are like removing that less than 0 when
yes.
So there you didn't mention the range, but without range you are getting this.
Yes, because after I have removed the -1, then I don't need to mention the range anymore, and it's automatically picking a reasonable value.
So those 1 or 2 like measurements for giving us the error in the beginning.
Yes, because remember they were actually, look at this value, -9,999. So there was just 1 object there, right? And so now the range of the histogram had to be between -10,000 and 30.
Okay.
When you divide this in 100 bins, it basically gives us that, all the objects really were squished in just like, the rightmost bit of the histogram. And then there was 1 all the way at the end, and everything else was empty. So luckily we have eliminated that weirdness. So now one of the typical problems that I have is that, we cannot fit these to sklearn algorithms. Right? Why is that? Yeah. It can take strings, right? This is something that, we can understand that, like a class is a class. Why would they care if it's a string or a number? But unfortunately, this works with array. An array means that we need to provide numbers. And so one of the most common things that we have to do is to re-encode the variables that we have, that in this case is a string, into a number. And so I'm using this like neat little tool called label encoder. And I can fit my data, which in this case is the class column of the data frame. And fit just means that it looks at how many values I have, how many unique values I have. So it decides how many numbers it takes. And then I do transform. And transform basically says, okay, since I have 3 possible values, I'm going to call them 0, 1, and 2. This is something that can be tricky. In 2 or 3 classes, it's almost always okay. But I just want to mention that when you turn strings into numbers, you are introducing a distance matrix that perhaps wasn't there. If galaxy is mapped to 0 and quasar is mapped to 1 and star is mapped to 2, you're sort of introducing the notion that galaxies and stars are more distant than galaxies and quasars, because the distance between 0 and 2 is greater than the distance between 0 and 1 and 1 and 2. So this, in general, in 2 classes is not a problem. In 3 classes like this, it's usually okay. If you're mapping several classes, this is something you want to have in mind. But this may mean that this is not the best way of remapping strings to numbers. So just keep it in mind. Right? Every time you turn strings into numbers, you're implicitly introducing a metric. But we're going to ignore this. And so, yes, please.
So how do you mitigate that when you have a number of things?
The way to mitigate that is you have a great, this also gives you the opportunity to use a great function called getDummies. So instead of encoding just like one label as like a 0, 1, 2, you can actually re-encode this as, is this present, yes or no? And then you have, and so this will give you like sort of like a multiple values target, but basically you would put like a cross of whether it was 1, 2, or another, and then you would just have like 3 predicted columns corresponding to each one of your labels. You can do something similar also for features. So there are ways around this that you may or may not need. Maybe everything is okay. I'm just saying, in the complex problem of like, finding, like improving your model afterwards, you may find that this is something that matters. Okay, so now I have transformed my class to a vector called y, and this is a way I can obtain the mapping, right? So I know now the galaxy has been mapped to 0, quasar to 1, and star to 2. But the array y contains only the values 0, 1, and 2. Then I can plot the distribution of the target as well. So which class is the most abundant? Galaxies, which were mapped to zeros, and then I have quasars and stars. Do you think this is something that we should? Is it worrisome? Does it mean that, I don't know? Does this come with a caveat? What do you think? Yeah.
Sorry, I guess I have a quick follow-up to
Please.
the last bit. Is there such thing as like a reshuffling of what you label, like the numbers, the data? Sorry,
You mean if you like to change this
you
mapping?
change the numbers, the mapping to maybe distance to have. Like,
Yeah, if you feel like this matters for you, yes, you can just remap a number to another number, right? If you feel like, okay, I think that these 2 classes are more similar. I mean, to be honest with you, this tends to be more of a problem when you are re-encoding features, because you are more likely to calculate distance in feature space. And so when it's on the label, I think it's less of an issue. So, but in general, though, nothing forbids you from, resetting it. For example, for me, I have to do it a lot of times. So when, let's say there's just a binary classification problem. You have two classes, right? And I think how this label encoder works is that, I don't know, it looks like the first and it calls it a 1. But in classification problems, usually the positive number, which is the 1, is associated to the object that is interesting, right? Because not all the metrics are symmetric in which one is the positive class. If you are, for example, like hunting for quasars, let's say that's relatively rare, right? You want that to be the one that has the 1. And so, I flip them all the time. Like, there's literally like this is just like a random assignment. And so you're very free to do something. And if there is one that makes more physical sense, then absolutely why not? Yeah.
Since in this data set we have more stars than galaxies, could that be an issue in how representative it is? Like, for example, in nature, since naturally there are more stars than galaxies, here it's the opposite.
I think here we have more galaxies. No galaxies mapped to 0. But in any case, let's assume that it was like the opposite thing. Could it be an issue? I think with, this doesn't need to be what's in the universe, right? This just needs to be, when we apply a classification scheme that is derived on this data to another data set. If that data set has a very different distribution of objects, could this be a problem? Absolutely, right? Because I feel like in the end, a supervised learning model learns example by example, right? So to some features, you learn to associate a label, but it also learns from the populations. And so one of the information they will learn is that, galaxies are more common. And so if you now apply it to a data set, which of course will have a different feature distribution that has a significantly different distribution target from this, it's not guaranteed that it will perform in the same way. So, I think the idea is like, does this need to be representative of reality? No, because this is just like a subset. But, when you look at, where are you going to apply this algorithm, then yes, definitely, it should be something like this. Yeah.
How can you learn the number of data points we're using for decision? Imagine we had like 10,000 black points in the area where there's only 10 black points. How would it know that there's like 4 black points? It's just like...
No, you're very right. It wouldn't know. But what I'm saying is that in general, a different distribution of these will correspond also to a different distribution of features, right? And actually, let me take it back. Let's say that we're looking at the decision tree, and let's say that you have a very imbalanced data set. Then, like especially if you have set a criteria where, you don't want things to be exact, it's very easy to get a model that just tells you, okay, there are no positive examples, and will have a very high accuracy. And you basically have learned anything other than the class distribution, right? So it may create the illusion that you have learned the relationship between the features and the output, but in reality, all it's doing is like, okay, I have a single partition, and my single partition has 98% accuracy, and for me, this is good enough. And so it wouldn't even bother looking at, but okay, here in this corner, you had a different type of objects. So, it really, it depends on the algorithm, as you say, but I think a lot of times, you have, you can accommodate learning just about, what is common and what is not common, and not necessarily, what is the correct relationship. Any other questions so far? So we have talked about imbalance, right? And so what this is telling you is like galaxies are more common. Now, is this something that we should keep in mind? Is my own question. And I would say in this case, I would call this something to keep an eye on, but it's not extreme, right? For 2 reasons. One, you have about 3 times as many objects in one class compared to the other. So it's not an extreme imbalance. I say that, every time you go more than 1 in 5, I think this is where you want to start worrying. And then the other thing is that this is still a data set with a lot of numbers. So the other problem could occur here if the numbers are so low that you start to have only like 10, 20, 30 examples in one class. we feel like each of them is like well populated, I would say 1 in 3 is not something that we need to really care about too much. Beyond 1 in 5 is where I call it a balance. Yeah.
Say this was a case where you had
like only one category, you're saying.
more or less, yeah.
Right, yeah.
Way too many, yeah.
Right.
That point.
That's a very good question. I think I don't think that there is a single answer. I think really what you do depends on, what your problem is, what your goal is. So you can do it. One thing that you can do is change which metric you look at. And so, the typical one that, when you build your first classification model, the metric that is returned to you by STLR is accuracy, which is just like the percentage of correct answers belonging to all classes. And so this is typically a problem if you have a very balanced data set, because if you now imagine that 95% of objects is in one class, you can have a completely dummy model that says every object is in that class. It's essentially useless, but it has 95%. So one possibility is to adjust your metric, right? What you use to evaluate the model. And say, for example, if you're interested in one of the less common classes, you can use a metric like recall that tells you out of the objects in interesting categories, what is the fraction that you have captured in your classification. So that's one possibility. Another possibility is to do this at the data level. For example, downsampling the class that is very common. So you can create, if you want to sort of give equal importance to all the classes in terms of, like how the information is learned, you could decide, okay, I'm only going to take a 10 of these, and I'm going to make a new data set that now has like a comparable amount of objects from all the classes, and this is like another way that you can try. Okay, so for now, I'm just remember that my target had 20,000 objects, but I only need to select 19,999 because I had eliminated one. So this is what I'm doing here. And then we can build the model. So one last thing that I like to do, again, very non-pro, is to sort of build some intuition on how different features are connected to the output variable. So you can calculate correlation matrices for this, just the correlation between input and output, but correlation is a very, very summary statistics. It's summarized so much that a lot of times it doesn't really tell you a lot. So another thing that I did here, since I only have 5 features, is we could make scatter plot for all the pairs of features, and I color the points by the label. What do you gain from this? Nothing but, if in some plots you get a very obvious gradient, then this tells you, hey, these features are good to separate out the classes. Or let's say, for example, we're using a decision trees, and you find that in some feature space, you have the things don't align horizontally or vertically, but maybe like, in a diagonal way, you can separate out the colors. Then this gives you suggestion for features that you could do. So again, these are not, solution steps, but I feel like it's sort of like, good practice just to build some understanding of how the data look like. And so you can see here, these are, like all the different combination of photometry. And so I don't see an obvious separations, but you can see that these gradients will definitely be part, and, like maybe some new features could definitely give you a handle on, like how to separate the colors better. And then finally, what did I put? Is there anything special that we can learn from these plots? And maybe a more interesting question is, based on this, do you think that we have good enough features? Now, of course, we should really see this in 5 dimensions, right? We want to see if the points of different colors separate out in 5 dimensions. We can't do that. So, one way is to build some unsupervised representation where maybe 2 dimensions are enough, but we're not gonna go there. But just with this, do you think in some of these plots, do you expect to be able to separate out objects of different colors? Do you think you may be able to do it with some noise? What's your expectation here? Do you think we can do quite well? Are you skeptical? Are you optimistic? I also realized I didn't put the light. Looks like the yellow must be the galaxy. Yeah. Oh, sorry, I had so her first. Yes.
I think the quasars and stars are separate.
Which the quasars are? Sorry.
So the quasars and stars are like separate clusters.
Okay.
And the galaxies like behind that, so I'm not sure what the other two.
Let me check the mapping. So the quasars are quasars are 1, galaxies are 0. So this means that galaxies and stars are yellow and purple, and then the quasars are the green. So this is, again, a projection. So we shouldn't take it too seriously, but I also think that it looks like the quasars, we can sort of like cut them out. But probably there are galaxies behind them. So what I expect is that we can separate out maybe some of the classes reasonably well, but there will still be some like confusion because especially the galaxies, they seem to occupy sort of like all of the feature space, while the other classes are more concentrated in different areas. Okay, so let's start. We have 3 minutes, so we can build the model. I think I accidentally erased a line when I say model equal GBG scripts. What is this? Neighbor classifier, yes. And then model.getParams tells me about the parameters I can play with. The most important one is the number of neighbors. If we do things at default value, I have 5. This line is to set up a cross-validation strategy. And so I have 5 folds. I shuffle them, and I'm fixing the random state so we all get the same. And then this is beautiful command, cross-validate. It basically creates the cross-validation for us. It builds 5 models. It saves the scores, like the test scores that are obtained on each of the 5 test folds, and then so that we can keep it, and we can also save the train scores. So we do this, it usually takes a moment. And the output of this is a dictionary. And so here we go. We have the mean train score is about 0.885. The mean test scores is 0.846. And we're talking about accuracy. So, we know that accuracy is slightly dominated by the more abundant class, but, not to the point of, I think, extreme worry. And then this is the standard deviation of the test scores. So what do you think here? The test score of about 85%, how is it?
Can you please explain the previous part? How
This?
Yeah, from there.
Yes. So when I use this command cross-validate, I give as arguments the model I'm using, which is my KNN with 5 neighbors, the features, the target, the cross-validation strategy. And the cross-validation strategy is the one that we have defined here. And so what it does is that it takes my complete learning set, looks, does a train and test fold partition, builds the model of the train set, calculates